Hello students. In this lecture we shall be talking about the techniques for nanomaterial synthesis. Nanoparticles for that matter, and we will first start with gas phase condensation. In gas phase condensation, the synthesis of nanophase materials can be done by evaporating a metal in an inert atmosphere. That's the first step. Then allowing it to condense on the surface of a cold finger, it is called. Then actually allowing it to condense on a cold, it's called a finger. I mean, it's a finger, we mean shape like this, which is actually kept at a very cold state. So the gas particles, the gas molecules, they get condensed into this cold finger and form the nanoparticles. So right here, gas, metal in vapor form. It is hot. They usually go and get condensed in this cold finger and form the nanoparticles. Now this cold finger that we talked about, this finger, this is kept cold by using the liquid nitrogen. And it's around 77 Kelvin. Approximately 77 Kelvin. Suppose we have formation of metal nanoparticles on this cold finger, and our aim is to form an ceramic, that is an oxide of this metal. So in that case, an oxidation process needs to be introduced. So oxidation to form the metal oxide. Is the ceramic. And after oxidation, it is compacted in situ, means during the experiment, and then followed by sintering. Now, this gas phase condensation, as we have previously told, is due to the evaporation of this metal in this inert atmosphere. And by inert atmosphere, we sometimes use argon gas for it, and evaporation is taking place, and the evaporation is taking place in an temperature regulated oven containing reduced atmosphere inert gas, and that is why it is also called inert gas condensation. Add a word inert to it, so it's inert gas condensation. So this is the first way by which we can produce nanoparticles. The second method is called DC arc plasma method. Now, in this method, the nanocrystalline alumina powders, let's say for example Al2O3, in powder form, they are synthesized by this method. So what we do is we apply a voltage of around 300 volts and 15 ampere DC supply at atmospheric condition by using aluminium electrodes. We're using aluminium electrodes, and it is kept in a closed chamber. So we have an aluminum electrode here, so we have in fact two aluminum electrodes, and there is a separation between the two of 3 to 5 millimeters, and they are charged differently. It means they are supplied by a DC. So one is the cathode and one is the anode. Let's draw it in a different way. So there are two electrodes, and they are kept in a closed chamber. One of them is the cathode, where oxidation takes place is the cathode. Let's take this as the cathode. This should be the anode. And this is the cathode. And there is a separation between the two. Of 3 to 5 millimeters, and this is the DC arc plasma with 300 volts and 15 ampere. So what happens is that there is an ignition taking place, between these two. So there is an ignition. Which is actually called an arc. uh, Arc is basically one of the states of a uh, gas glow. That means if you plot temperature versus current, I versus V, then usually it takes a form like this. So this is the place where the arc takes place, and this is the Townsend region. So when this condition is reached, or arc plasma for that matter, plasma is a state where the positive, negative, and the neutral species are in equilibrium. So mean by plasma is the positive, negative, and the neutral species are at equilibrium. Now, whatever powder is deposited, whatever powder is formed, is deposited in the inner walls of the chamber. So this is where the powders are, aluminum powders get deposited. You can mention the arc here. So this is how this is where the arc deposition is taking place. Now, after this deposition has taken place, we offer cooling of the interior, and that the powders are gently scrapped from the roof of the chamber and collected for analysis. Mainly, it's on the roofs. So this is the second way by which we can produce nanoparticles, especially alumina. And now the third technique is called sonohydrolysis of alkoxide precursor. Now, through this technique, nanoparticles of gamma phase alumina can be prepared, and their average size is 5 nanometers, which has been found. So what we do is we do the hydrolysis. We hydrolysis of an alkoxide precursor, and the alkoxide precursor is aluminium isopropoxide. So L tri iso alkoxide. So in short, it's called ALTSP. So this is subject to an ultrasound of power 100 power density 100 watts per centimeter square, and it is under the influence of formic or oxalic acids. Which are in fact called peptizers. And after this ultrasonic treatment, the next step is the calcination. So it is also called an ultrasound driven cavitation process. Write it as ultrasound driven cavitation process. And it is so what happens is the mechanism in fact is the agglomeration of interparticle hydroxyls taking place. So it's agglomeration of interparticle hydroxyls. The formic acid, which is the pepticizer, is shows a lesser degree of adsorption on the surface of the precursor nanoparticles. So the ultrasonic driven agglomeration, as in this case of the primary particles, and also the role of organic modifiers on the microstructural properties of the precursor and the target aluminum phase have been studied. So now we come to the next process. It is called ultrasonic flame pyrolysis. So in this method, non-crystalline alpha phase of alumina are mainly produced. So we start with aluminum nitrate, which are subject to ultrasonically dissolved in methanol water mixture. This aluminum nitrate is dissolved in this ultrasonic treated non-water mixture, and then it was pyrolyzed. The next step is the pyrolysis. pyrolysis in an oxypropane flame. This pyrolysis takes place, and this actually leads to formation of this alpha Al2O3 that we see. It's also called flame aerosol technique. Flame aerosol technique, and it's called FAT. So similar to this technique, we have another technique. It's called flame spray pyrolysis. FSP. So where the liquid precursors are burned. So instead of aerosol, we are using here liquid precursor. Which are sprayed and they are burned. So this is usually the conventional technique, but the latest one being this technique that we usually talked about, that is using the ultrasonic flame pyrolysis, or UFP for that matter. Now the advantage of this method is that the ultrasonic acts as a nebulizer. To atomize liquid into spray. Atomizes the liquid into spray. So these liquids are in fact in micron or submicron range. So micron or submicron range, the liquid. So using this ultrasonic technique, what it does, it atomizes that, it actually reduces the particle droplets or the droplet size. So that is the advantage of this technique. Now these droplets are then, so we have droplets are then fed into an oxidizing stable and premixed burner. So there is an oxidation taking place, and they are then used to form the propane flame that we have talked previously, this oxypropane flame. And as the liquid traverses the flame, it is stripped of the organic and solvent components. So this liquid precursor, it loses the, we should say, stripped of organic and solvent components, organic and solvent components, and a metal oxide cluster is generated in the hot zone. Which ultimately which actually ultimately clusters or coalesce into oxide nano-sized particles. Nanoparticles. And it is done on a copper substrate. And this copper substrate is kept in the nebulizer tip. And whose distance from the boundaries are distinct. So let's try to understand the whole process. First of all, this is the liquid precursor we talked about. So this is the liquid precursor. Now we provide an ultrasonic nebulizer, and we also provide a burner. It is a burner. Okay, and there is a copper tip associated in front of the nebulizer, and we are supplying ultrasonic sound here, and there is an so this burner is the oxy propane flame, call it an OXP. The distance between this nebulizer and oxypropane flame is adjustable. So what it does is that it allows this, it first atomizes and allows this liquid precursor to travel, then it gets flamed here, and then it gets condensed onto this copper substrate which is kept at the tip, and we get the required ammonia powders. And these powders are then scrapped from the copper tip and sent for analysis. So what are the variables which can be adjusted? So there are a few variables. The first variable is the flame parameters. That means the voltage, the current, or the distance. The second variable is the droplet residence time. Now it is important because, as we have told, that these metal oxide clusters, they coalesce. So the time given for the coalescence is important, and it will determines the size of the nanoparticles. And lastly, we have this captured distance. That means the distance between the nebulizer and the burning region. So these three things are important to obtain uniform sized nanoparticles. So for uniformity, and apart from alumina, this method has been used to reduced down to crystalline titania. Then zirconia and alumina. We've already talked about alumina. So all the metal oxides, important metal oxides in ceramic form, have been produced by this UFP method.